everyone, in this video, we are going to solve a problem about the radiation heat transfer. Here is our problem. A uniform temperature of 250 degrees Celsius is kept in a spherical cavity with a 2-meter diameter. Now, a 10-millimeter diameter hole is drilled. Calculate the maximum rate of radiation flowing through the hole. And what would the answer be if the hole had a diameter of 0.5 meters and a temperature of 500 Kelvin? So what are we going to calculate in this problem is the rate of radiation flowing through the hole. In A, 250 degrees Celsius and 10 millimeter diameter, and B, 500 Kelvin and 0.5 meter diameter. Rate of radiation heat transfer is given by the equation Q dot rad equals A times sigma times T raised to 4, where A is the area, sigma is the Stefan-Boltzmann constant and has a value of 5.67 times 10 raised to negative 8 watts per square meters Kelvin raised to 4, and T is the absolute temperature of the surface of the body in Kelvin. Now, let's solve for A. For A, we'll given of diameter of hole equals 10 millimeters and a temperature of 250 degrees Celsius. As you can see in our problem, we also have the 2-meter diameter. But since we are calculating for the rate of radiation flowing through the hole, therefore we use the diameter of the hole. Now, we have the equation Q dot rad equals area times sigma times temperature raised to 4. Note that the area for hole is equal to pi times the radius squared, and the radius is equal to diameter over 2. Now, calculating our area, we will get pi times our diameter, which is 10 millimeter, which is also equal to 0.01 in meters over 2 squared. We will get 7.854 times 10 raised to negative 5 square meters. Now, plugging in into our equation, we will get Q dot rad equals 7.854 times 10 raised to negative 5 square meters times our Stefan-Boltzmann constant, which is 5.67 times 10 raised to negative 8 watts per square meters Kelvin raised to 4 times our temperature, which is 250 degrees Celsius, and since our temperature should be in Kelvin, therefore we add 273 Kelvin raised to 4, and we will get Q dot rad equals 0.333 watts, and this will be our answer in problem A. Next is solve for the Q dot rad, or the rate of radiation at the diameter of 0.5 meters and temperature of 500 Kelvin. So to solve for this, we will just use or do the same process. So we have the given equation of Q dot rad equals area times the Stefan-Boltzmann constant times temperature raised to 4. So plugging in all the given values, we'll get Q dot rad equals pi times the diameter 0.5 meters over 2 squared times our Stefan-Boltzmann constant 5.67 times 10 raised to negative 8 watts per square meters Kelvin raised to 4 times our temperature, which is 500 Kelvin raised to 4, and we will get Q dot rad equals 695.81 watts, and this will be our answer in problem B.